Welcome back, everybody. Today we're going to be talking about the Poisson distribution. The Poisson distribution was named after a French mathematician from the 1830s who saw its applications and worked with it quite a bit. Now, the Poisson distribution, all right, is kind of similar to a binomial. All right, we'll describe the number of events occurring in a fixed time interval or region of opportunity. A couple of classic examples. Number of emails in a year. Number of chips in a chocolate chip cookie. Or third, number of earthquakes in the U.S. in a year. Just a couple of classic examples. All right, here are a few more examples of the Poisson distribution. Number of messages arriving at a telecommunication systems in a day. Number of flaws in a meter of fiber optic cable. Number of radioactive particles detected in a given time. Number of photons arriving at a CCD pixel in some exposure time. And the formula for a Poisson distribution is P, that symbol's a lambda, is e to the negative lambda, lambda to the x over x factorial, all right, where lambda is equal to our average is also equal to our variance. That's one of the special pieces of your Poisson distribution. X would equal 0, 1, 2, however amount of occurrences we're looking for. And E is our natural number, approximately equal to 2.17183 ... All right. So let's take a look at this next piece and let's try to decide if we have a Poisson distribution or not. So first one, number of duds found when I test 4 components. Number 2, number of heart attacks in Brighton in a year. Number 3, number of planes landing at Heathrow Airport between 8 and 9 a.m. Number of cars getting punctures on the M1 each year. Number of people in the UK flooded out of their homes in July. So why don't you guys pause the video for a minute, think about it, and see if you can decide, is it Poisson, is it not? All right, hopefully you paused the video to think about these for just a second. Let's run through them real quick. All right, so the first one, number of duds found When I test for components, I would say this is not a Poisson distribution. I think this looks more like binomial to me. All right. So let's say number 2, number of heart attacks in Brighton in a year. Heart attacks are definitely independent events. Just because one person doesn't have a heart attack doesn't mean the next person is more or less likely to. So I would say yes, this would follow a Poisson distribution. Also, it has a large population, all right? That's one of the things that you look for in a Poisson distribution. All right. So number of planes landing at Heathrow between 8 and 9 a.m. Definitely a large population. There's a lot of planes going to Heathrow Airport. However, it's not necessarily independent. Planes don't get to land whenever they feel like it. They are definitely scheduled. Also, between 8 and 9 a.m., there's going to be a lot of planes landing at Heathrow Airport versus 1 a.m. to 2 a.m., where there definitely would be much less planes scheduled for that time. So I would say that this is a no. All right. So number 4, number of cars getting punctures on the M1 each year. Well, the M1 is a stretch of road, and whether your car gets a tire puncture depends on the wear of the tire. So I would say that that is definitely an independent event. Just because your tires get worn out and I replace mine more frequently than you replace yours, all right, means that I would get less punctures than you. So I would say that this is a yes, because the M1 definitely has a large population, and as we just said, would be independent events. All right, so number 5, number of people flooded out of their homes in July. Well, home floodings aren't necessarily independent, right? If it rains in the UK, and let's say a home in London gets flooded, doesn't mean, it probably means that more than one home in London will get flooded. So not necessarily all independent. Floodings don't typically happen, so I would say it's probably a small population as well. So I think I would consider this a no. So the key here is that if you can identify a Poisson distribution, typically the formula is not too hard to manipulate. All right. So let's move to our first example. If there are 200 typographical errors randomly distributed in a 500-page manuscript, find the probability that a given page contains exactly 3 errors. All right, first you need to find the mean number of errors. So I'm going to give you a hint. With 200 errors distributed over 500 pages, each page has an average of how many errors? All right. So hopefully that you worked it out. That lambda, which is your average, is going to be 200 over 500, which is 2/5, which is 0.4 errors per page. All right, so we want to find the probability that a given page has exactly 3 errors. So our x in this case would be 3. So I'm looking for p of 3, given our lambda of 0.4. And let's fill in that formula. So it's e to the negative 0.4. I can just fill in lambda. 0.4 to the third power all over 3 factorial. So why don't you guys at this point pause the video, run this through your calculator, and I'll catch you on the back end. All right, I got 0.00715. All right, which means that there would be less than a 1% chance that a given page would have exactly 3 errors. All right, so let's take a look at the next example. All right, the next example states, on average, lightning kills 3 people each year in the UK. So in this example, I'm giving you lambda. Lambda equals 3 on average. What is the probability that it only killed 1 person this year? All right, so again, this follows a Poisson because lightning is certainly random. All right, so if lambda equals 3 and x equals 1, let's fill in our formula and see where it takes us. So probability of 1 with lambda of 3. So it's e to the negative 3 times 3 to the first over 1 factorial. All right, so why don't we pause the video, put this into your calculator, and let's see what we get. All right, well, I got 0.149, which is a very low probability. All right, so let's try the third example, atomic science. 1 nanogram of plutonium will have an average of 2.3 radioactive decays per second, and the number of decays will follow a Poisson distribution. So here I'm telling you it will follow a Poisson distribution. What is the probability that in a 2-second period there will be 3 radioactive decays? All right, so why don't you guys pause the video and start by thinking about what your lambda might be. All right, well, hopefully you identified our initial thought would be that lambda would equal 2.3 decays in 1 second. However, we want to know the probability in a 2-second period. So I would like to change my lambda, make a new lambda that deals with a 2-second period. So what's the average radioactive decays in a 2-second period? It would be 2.3 times 2, 4.6 radioactive decays per 2-second period. All right, once you identify that, and we also identify our x, which is what's the probability that in a 2-second period there will be 3 radioactive decays, so x equals 3. We can then fill in our formula. So why don't you pause the video, fill in the formula, and I'll see you on the back end. All right, so P of 3, Oh, our lambda is not 2.3, it's 4.6. Equals 4.6 to the third power, e to the negative 4.6, right? E to the negative lambda, all over 3 factorial. All right, so why don't you run this through the calculator, and we'll see what we get. Okay, well, hopefully you got 0.163, because that's what I got. And okay, that's it. All right, so I've got 1 or 2 more examples. Let's try this one. All right, students enter the university center at an average rate of 20 per minute. What is the probability that in a randomly selected five-minute period exactly 90 arrive? Now, by looking at this problem, you're going to jump right in. You can say average rate of 20 per minute. So lambda equals 20 per minute, right? And then we need a 5-minute period. So your new lambda would be 100 per 5 minutes. However, my suggestion would be to slow down, because the independence here is kind of questionable. First things first, entering the university center. More students will probably enter the university center around lunchtime than will late at night. Also, the randomness comes into play, because in a typical university, students don't enter at a truly random pace. They will enter 3 or 4 at a time. You'll have a couple of people coming in, 3 or 4 at a time, because they're friends, they're getting lunch, they're going to the bookstore. You would have an occasional person going in on their own, but usually there's a lot of clustering up. So the independence here is questionable. I wouldn't necessarily jump right into a Poisson distribution unless the problem told you that it follows a Poisson probability. Okay? Let's try the last one now. All right? So the last one. Suppose a fast food restaurant can expect 2 customers every 3 minutes. Two customers every 3 minutes. on average. Got to put that in. On what is the probability that 4 or fewer patrons will enter the restaurant in a 9-minute period? All right. So let's talk about a solution. We're going to start with our lambda, which is 2 customers in 3 minutes. How many in 9 minutes? Well, multiply times 3, so we get 6 customers. So our lambda is right here. All right, well, now this question is changed a little bit from our last one. Our last one was exactly that amount. Now we want 4 or fewer. So if we want 4 or fewer, we want the probability of 0 patrons plus the probability of 1 patron plus the probability of 2 patrons plus the probability of 3 patrons plus the probability of 4 patrons. You may look at this thinking that it's a lot of work. However, if you just fill in the formula, it becomes very, very manageable. So why don't you take a minute, pause the video, fill in the formula for each one of these x's. All right, hopefully you paused the video. So let's start filling in our formulas. So I have my lambda is 6, and each one of these is going to be my x's. So there's x, there's x, there's x, there's x, and there's x. So 6 to the 0, e to the negative 6 over 0 factorial plus 6 to the first, e to the negative 6 over 1 factorial plus 6 to the second, e to the negative 6 over 2 factorial, 6 to the third, e to the negative 6th over 3 factorial plus 6 to the fourth, e to the negative 6th over 4 factorial. So I would write out each one of these and then just put each one into the calculator separately, all right? And write down each individual result. So why don't you do that now? Why don't you pause the video, put each one of these into your calculator, and then we'll compare our results on the back end. See you soon. All right, hopefully you paused that video, and I'm going to give you my results. My results were 0.0025 plus 0.0149 plus 0.0446 plus 0.0892 plus 0.1339. All right, one last time. Pause the video. Let's add these up. All right. I added them up. I got 0.2851, or if you want to put it in percentage, would be 28.51% chance that 4 or fewer patrons will enter the restaurant in a 9-minute period. And I would like that sentence at the end. All right, that's what I have for the Poisson distribution. Hope you enjoyed, and I will see you next time.